Thank you very much, Dino, for this nice introduction and for this invitation. So what I'm going to present today is mostly the, in terms of open source, 15 years of experience in doing open source development. And we have a tight collaboration with Robotics indeed, because they are very open in terms of models and low-level access. And so we did together a European project called Memo. We just finished it this summer. And I will briefly give you some highlight on these results using the stack of systems that we are using. So, well, my group is here, so I would like to acknowledge, because everything that I will present is really a teamwork. I think this is the stuff. I think right now doing humanoid robotics alone is extremely difficult, and this is why I think open source and taking into account education. Also, what I will mainly show here is for PhD or postdoc, is the feedback that we have on simplicity and efficiency in terms of usage. So just for the group is we are located in the south of France, Toulouse. So we have 260 days of sun. So if you like to join, we are looking for nice, bright researcher. So we have either join CNRS. It's a very nice permanent position. You're never going to get rich in CNRS, that's for sure. But you have a lot of freedom to pursue your scientific goals. And we're going to start a new project with Robotics. We have a joint lab, which is going to start soon. Also, we still have some administrative stuff to do. And I will open very soon a postdoc position, which is completely related with Baymax. So it's with Gordon Cheng, who is doing one of the, to my taste, one of the best skin actually, and he will be able to sell it. And our goal is to put skin on the Talos robot here, built by Robotics, and which will be presented by Francesco this afternoon. And I have to say that Talos resembles a little bit to Baymax, at least with the color in terms of size and power. So we are 30 persons, 8 permanent researchers, 4 CNRS researchers, and we have 20 students. So what we are doing is we are mostly working on the science of anthropomorphic system, and we are very, very focused on using a model, motion planning, task hierarchy, and learning, and we cast all of this into optimization problems. So actually, we see really the fact that there is big connection, for example, between reinforcement learning and model collective control, thing that I will talk a lot. And there is some very interesting bridge to do together. And we apply this on 2 big fields, complex robots such as humanoid robots, but also in biomechanics, which I think is also an interesting topic in humanoids. Also, I won't talk about it right now. So we focus on this. So the main output and of the group is software system, which are almost all open source. So we have a planning system called the Humanoid Task Planner, the stack of tasks, the task space inverse dynamics, Pinocchio, and Crocodile that Gino just mentioned, which is a whole body model predictive control. So why we develop using open source licenses is, for us, the main point is reproducibility. I think this is extremely important. And the point for us is that other scientists can actually reproduce, analyze, argue, and very often disagree with what we wrote. And we found out that very often having the code is a necessary complement to paper to know what people really implemented into the system. So sometimes you see very big differences between what people actually implemented and what they describe in the paper. We also think that it's, given the current times, it's a frugal way. So you avoid people redoing the same thing over and over. Also, I do appreciate that sometimes it's needed to implement, to learn. Still, usually it takes half a day to implement in Python an algorithm that you find from the textbook. Having a software which that you can deploy and provide everywhere, most of the time it's 2 years of work. So really on this one, I think it's really nice that we can work together on this kind of a common tool. And what we find out also is that well, it simplifies the intellectual property. And for example, we have 2 industrial partners, and all the problems of IP were solved using very business-friendly licenses, such as BSD Clause 2 or Apache licenses. And for us, we also found out that it increases the scientific impact of our system. So, but the point is that very often people think open source is free, which is absolutely not the case. And most of the times, just taking a software like this, the research software needs people with a sufficient skill to use them. For example, for us, it's C++, Python, ROS. And even so, we are trying to lower the barrier. It's really difficult to have people able to contribute PR and source. So, and finally, understand that some people, when they're doing a contribution, it may have some impact, and we need to actually forecast about the application, the impact of the modification that we are doing. Now, there is another point with what I call the software research paradox, is that most of the times, when you want to do a scientific contribution, it means that you have to think differently than before. And what happens is that usually when you do a software architecture, you have actually a software in mind or an approach in mind. And well, building on top of the system often means breaking the software architecture. And this is my experience is something that I found that domain-specific languages is very often not a so good approaches, because you are narrowing down the capability of people to go out from the software. So what we did is actually making something very simple. We do mathematical prototyping in Python, and once it is done, it's fixed. We know that the math are correct. We do an efficient implementation in C++ and do Python bindings to reuse what we've done before. And this will increase a lot the efficiency of the students, and being very, very careful in separation of concern. That some people, very often, I see people mixing mathematics and ROS. Please don't do that. We really have to separate math and ROS. I mean, you have a lot of big companies like Boston Dynamics. If you look at Agility Robotics, they don't have ROS inside, because actually it's nice ROS when you do integration. If you do motion control, most of the time it's a burden. So we are trying to separate all of this, and we do it at the later stage. And as I mentioned previously, I strongly recommend ROS control. So going back to the classical structure of our control system, here you have a kind of layer classic structure that we have usually when we do motion generation of robots. So you have the whole body instantaneous controller, which is nowadays cast as a QP solver, either using a hierarchical solver or a mixed objective function. You have a stabilization loop based on a state estimator using the sensor. On top of this, you have a central dynamics where you generate center of mass trajectory, which are dynamically stable using model predictive control. And these are driven by a motion planning system given constraints and sequence of contacts based on SLAM and SCP map. So on top of this here, I highlighted some of the systems that we're providing. So for example, here, the humanoid path planner, which is actually creating automatically a finished state machine, is sent to our whole body controller called the TSID, which was recently used by several people. And we have Crocodile here that you can use from central dynamics, but also another approach that I will describe later on quickly, which is whole body predictive control. So the point is that very often here, when you just consider the central dynamics, you don't take into account all the limits of your limbs, which have a strong impact, such as Stasse, for example. He has heavy arms, heavy legs. And for example, it can have an impact of modification of 5 centimeters on the center of mass trajectory. So it has to be taken into account. And this can be done with a whole body model predictive control, such as the one, for example, Mujoko, back on the ELQR algorithm proposed by Emotodorov. The problem is when we do whole body model predictive control, the space of trajectories that you have is so huge that you are extremely sensitive to the warm start, your initial condition. And if you do the classical way, assuming that you know nothing, you start from zero, and you let the system try to find a solution, most of the time the system breaks. So you need a memory for that, and this is where learning is coming into play. So let me show you briefly what some experience that we have. We presented this to ICWA last year. So this is an experience that we have done already on HRP2 that we have redone on Talos humanoid robot. So what's happening here is that you have a whole body MPC running at 100 Hertz with a 1.6 second horizon, and you take into account everything. all the dynamical constraints. And here, the person is just controlling the robot with a blue square, which is the center of mass, and you let the system go down. So you have the closed loop, you take into account the system, and what's happening here is that you let the system try to follow this blue square with just the hand effector. And what's happening is that we put geometrical constraints here that the system should avoid self-collision with the bar and the forearm. The system, if you let the system having no information on this, most of the time using classical Akado system, you fail 50% of the time. If you use a simple k-means as memory, then you go up to 98% of success doing this in real time. This is where memory is interesting. Now, the drawback with this is that as it is torque control, so we are using using DDP to solve the problems, and DDP gives you feedback gains, and we are sending the feedback gains to the low-level control at 2 kHz. So the torque control is trying to solve the torque references at 2 kHz, thanks to and it's provided by Robotics. The problem is that you are not following the system, but then you can really be much more safe. So here you have a physical interaction, and this is something that you cannot do with a position control robot, the classical electric ones. And then the system is much more efficiently safe. Now, as I told you, torque control most of the times, the drawback that you have is that you are less precise in terms of trajectory following, and this may impair the quality of the working. And to avoid this, what we have to do is we have worked on a lot on the cost function shaping, and now we are able to work with a robot. So here it's we have a reduced size. So we block some of the body robot, and we are able to generate a working pattern in this on the robot. So it might be actually not super nice, but actually with this robot we had a lot of trouble. With the classical approach, because you are very sensitive to the modeling of the system. So if your model is wrong, and actually we have flexibility problem with the robot, then it took us 2, 3 PhD, 5 years of work to make the robot work in torque control mode. Here, with this model MPC, we had the students being able to do the motion in less than 6 months, and we had 3 other students doing torque control, sanding, for instance, with the robot, trying to go toward a precise motion, thanks to this whole body MPC. And this is an application to stairs. So of course, this is not Atlas. I tried to buy Atlas actually, but Robert says no, because it's too you need a full team to be able to support the system. And we are closer to Barcelona. So everything that is done here on the system, you can redo it on the robot. You can buy it. It's kind of expensive. It's $1 million. But still, it's open source. And the nice stuff is that you can use the working pattern generator provided by Robotics, or remove it if you're not happy with that. And this is again something that you can do thanks to Rush Control. So to go a bit fast on the algorithm, so it's a very classical optimal control over an horizon with a cost function and a dynamics. So what we did first is an implementation taking into account the sparsity of the parents. I think this is something very specific to our robotics problems. So we focused on the optimal efficiency with this statistic implementation, and we ideally implemented a simple algorithm. And then what we did is we added secondary functionalities like constraints, and then we had a choice either to do projection-based approach, like what is done on Akado with SPT-like problem, which tends to be very stable, but also very inefficient. And we don't think this is appropriate in robotics. So actually what we did is we use a penalty-based algorithm with augmented Lagrangian. And based on something which is extremely important is to have a very, very fast dynamical library. And I think one of this library called Pinocchio is very well known right now, or has a lot of success. And it is done thanks to the fact that we re-implemented 5 times. Okay, tried different kind of, we used the Mathematica to generate automatically the code, and we did the template programming, found out that we could use very nicely actually simplify the code to make it more accessible, and use better the capability of the processor to guess what will be the next iteration. And thanks to that, we go down to, for example, 5 microseconds to have the whole body dynamics. And here you have numbers for the inverse dynamics, mass matrix, and the core dynamics, even for robots such as Stasse. And then using this and code generation, you can have very fast system. And what we found out is even using the new ARM-based processors, such as the M1, M2, and maybe the new Qualcomm processor, what we expect another increase in terms of speed for Pinocchio and Crocodile. So now, based on that, with Crocodile, what happens is that when you fix the phases, so compared to Mujoko was able to discover the system, but what we found out is it gives you, because of the convexification of the contact, unfeasible, or something which is not very good with the dynamics of the system. So we keep rigid contact, but we specify the phases, and you have this very nice video when you specify the phases, and you give a good initial guess. The system is very quick to find a solution for various kind of robots, not only robots such as Stasse here jumping, but also here you can see the animal robots. And we also have, for example, the HiCub that is able to generate some motion. And what is interesting is that we copied so that the system is able to deal with non-feasible initial solution. But if you are very close, the system is able to correct it very quickly and find a one which you can try and which is coherent with the physical system. So here we're able to go to up to 50 Hertz on ICAM, 100 Hertz in the real Talos robot, as I shown you, and you can go up to 2 kHz on the 9 degree of freedom kilohertz. So this can be applied to industrial robot without any problem. So what we were able to do with this test robot, on this robot, which I found to me is the right level of openness, in the sense that we have this force control approach, which allow me to have access to the robot up to 2 kHz and removing the controllers of the system, because cross control gives an abstraction of the controllers. So if I want to use the one from Paralytics, which is closed, fair enough, I can use it, but if I don't want, I can remove it, which you cannot do most of the time in this format. And which is super nice. So what we did is we actually collaborated with Pararobotics using their own inverse dynamics, but using our own stabilizer and the central dynamics model predictive control. And so, and we are able to reach this level of work. So I'm super proud of this. I think you see the length of the steps, but they are super wide. It's almost 50 centimeter steps in torque control mode. Actually, for me, the best ones are the one from DLR, and we almost reach the same speed and they have with the same kind of structure. So we are, which means that now with a robot that you can buy, you can also do torque control, whole body torque control on the system. And normally, what we found out is because we have the first one, it's a prototype. So this is the one who is the worst actually behaviors. So you should be faster if you buy a new one, which will be better. So it's going to be presented tomorrow at 9:50 by Meryl Villa, who did a robust control approach in this project. So, and to briefly conclude on this part, the point is that all of these are very much model-based, even if you use memory. So you are very sensitive to actually the compliancy between your model and reality. So we find out a way to cope with the flexibility by identifying it. But the main problem that we have with Talos right now is that because of the limitation of the power electronics, actually the torque sensor, you have torque sensor. This is because we specified it like this. They are not feedback to the low-level Elmo board here, as it is done in Toro, but to the main CPU, which gives you a very low bandwidth, which is evaluated between 20 Hertz. So it's good enough to have the robot work, but it should be better. So what we have done is with Thomas Flyol, so it's a joint work with the Max Planck Institute and YNU, we are doing open hardware. And as Chris said, we also believe that having accessible hardware is very important. So we did this, this system, you can find everything open source, the mechanics, the power electronics, the firmware, and the software to control the robot are fully open source. So here, this is our implementation. So the power electronics was done by Thomas Flyer, our postdoc here. And we have used it for doing torque control on the system. And because we have a very good match between the model and the system, so it's done on the paradigm of having a kind of direct drive system, we're able to, on the right, you have the robot where we did actually reinforcement learning on the system, completely on the cloud. And we were able to run it on the robot with zero shot, zero modification. And I believe it's because we have a very good match between the model and the simulation and the real hardware. So, and the real hardware. I think this is because we can control what we put inside the system. I'm not sure it's completely accessible, or we cannot scale it. So this direct drive system means that we need to have very big motors on the system. So probably it's not feasible at the humanoid size, but it's an interesting topic. And now what we are trying to do is to have the same. So Thomas is making sure that this robot is very easy to use and that you can understand everything. So he's using Python to access directly on it. And what we're trying to do is to simplify the software pipeline from this robot, which is super easy, costs 10K, you can break it, you just have to reprint the system. Well, you need specific tools to do it. Again, it's open source, but not completely free. You can buy a kit to PAL Robotics, and I think there is an Israeli company which also is selling some kit. And my aim right now is to make sure that the software that we're developing here can be easily put on the humanoid robot Talos. So at least for me, so the take-home message that I really believe that open source software and hardware are increasing a lot scientific reproducibility. To give you an idea, 1 month ago, Michael van de Pan published a video where he actually bought a kit, installed it, and make the robot walk on 2 feet. So I was super jealous about that. But this is super nice. It increased really much the impact of what we're doing. I think it speed up research, decrease the overall cost, and this is not against business as I've shown. I think Airbus and big company are very it makes sense for them sometimes to have open source. And when you want to hide it, if you do it properly, again by separation of concern, you can do business with. Thank you very much. If you have any questions.
So, any questions?
Thank you very much for your talk. So when you look at the simulation environment and the physical hardware, what do you think are some of the biggest challenges to download whatever you train on simulation environment directly to?
Actually, I would say that so for rigid body dynamics, it's almost we have the equation, it's working quite well. Problems comes when you have flexibilities. Right now, the big problems is where do you put the flexibilities, and this becomes kind of an optimization problems of higher orders. So where should I put it? How can I identify it? And what happened is that in terms of simulation, the direct impact is that if you want to simulate properly a spring, you have to increase the step size of the simulation by 1,000, which is super costly. And I think there is the work of DLR again with Alina Buscheffer on springs, which I think it's interesting. So that will be the first part of my answer. The second part is the dynamics of the actuator. When you do torque control, this is extremely important. Well, it's usually completely killed when you do position control. You can forget about it. But when you are doing torque control, you get all the nonlinear dynamics of the harmonic drives in the face, and this is making the things much more complex.
We can say about the future bit 1 of 10.
Yeah.
So I think it will be the body sensor.
Yeah, so we're gonna use the taxel that he wrote, and the main idea is now to put the taxel on the upper body. And what we'll try to do is to do a whole body motion generation using the feedback of the skin. And there's plenty of nice points with that.
So how do you foresee the integration of the body sensing into the control?
So what we will probably do is, so the main problems is that you increase the complexity of the problems by the number of contacts that you have to take into account. So we'll work on how we can simplify it. And what is, so very often is you want to avoid singularities. So for example, with simulators that we have in control, when you have B lateral contact, they are often becoming unstable. So this kind of numerical things will have to be taken into account.
How many modalities do you think is enough for the fix?
Oh, interesting question. I don't know. We start to have a lot of very nice ideas, and I'm pretty excited about this project. I think there is interesting things, but we have to think in a very different way. I mean, maybe it's not going to be human life, but I see some very interesting things.
Okay, thank you. Yes.
This is Chris Hackson. So
Yep.
There are two sources of dynamics. One's the robot, the other's an environment. In legged locomotion, we typically trivialize the environment dynamics. We say it's rigid or something. But in manipulation, it's the environment, including objects and all that stuff, dynamics that matter. And the dynamics of the robot are secondary. So it's a whole different ballgame. So how are you going to extend this stuff to manipulation?
Okay, so I have a video on the manipulation, and we took it, we simplified it. So we are able to do manipulation. So here, so this is for that. So here you have the human robot in front of a box. So you know the box, you know how to handle the box, you know his model, and what you have to do is to swap the box upside down. Okay? And here we trivialize the dynamics in the sense that we just want to fix one premise: is what is the sequence of control that you have to do in order to swap this box upside down. And usually what's going to happen is an integrator will write carefully by hand with this Finite machine. And actually, just by providing a kind of simple relationship between the fact that you give the affordance of the object, the robot has some affordances, and we explore these affordances, this actually Finite machine is going out of the automatically from the system. Everything embedded into the robot, less than 2 minutes. And actually, they are really controls, because at the time that we did this, we had problems with the geometrical identification of the robot, and we really had to do visual servoing to actually take into account the real state of the system and the robot. And actually, the robot is doing these sequences, actually doing controls. So I would try to extend this approach with more complex dynamics. Also, it's probably going to be very complicated. So this is why we're also exploring reinforcement learning to actually prune down what are the solutions for this kind of problems. So I would say for simple manipulation like this one, we have already something which looks like it's working. I hope I partially answer your question.
So, new question. When you have deformable objects or liquids or granular materials, abstraction of the dynamics becomes very important. Because what are you going to do? Simulate the whole finite element analysis? That's going to be grindingly slow. So how can we automatically abstract dynamics?
Okay, so some of my colleagues back in France, maybe there is some other simulators, but I know this one, and I think it was used, presented at IROS in the soft workshop 2 months ago. It's SOFA, and SOFA is using a GPU because finite elements is something where GPU shines, where you can actually simulate very quickly the state of the deformable object. So practically, I will go down that road and try to see how the robot can interact with this soft deformable object and use classical approaches such as the one that I show, but using this GPU-based finite element simulation, which is almost real time. Does that answer your question?
I'm very skeptical. I mean, I heard your answer. I understand what you say. I don't believe it will scale. You know, if we talk about making a bed, are we seriously going to be simulating all the cloth at full detail? If I add more cloth, are we going to add more computational cost?
That's a good question. But again, if you look at the massive computational power that we have inside the brain, I think GPU is pretty inefficient, but again, with the proper hardware, looks like it's not that stupid. I would say again, I will bet for the new breakthrough that there are in ARMS in GPU, lowering the cost. I think it's not so much, and I agree that there is some question about what would be the size of the problem that we have to solve in order to be practically efficient. But I will bet on this direction.
Just to build up on that, as opposed to just primitives.
Yeah.
This, as opposed to just a primitive where you have some learning action to flip something, and it's just almost a function call.
Yeah,
As opposed to calculating these complex and.
Yeah, but you know the problem that I have with this is one way, but for me it's like it's still optimization with the model, because most of the time when you do reinforcement learning, you do reinforcement learning on simulation, which are model. So in simulator, so of course, yes, if I have the model, I can train the system to have a reinforcement learning system or any neural networks doing shortcuts on the model. Then can be very efficient. Yeah, sure. But I would say this is a classical toolbox. But I will go first for the model, and when I know it, I understand it, I know the size, then I try to learn it to have a shortcut. And I didn't show it here, but this is almost what we have done in its memo project that was about this.